But you've made it and you've shown up for class, so well done. It's supposed to get up to a nice warm temperature this afternoon. So in between all of the important studying you have to do, make sure you enjoy some time outside. Okay, so today we are wrapping up topic 3.4. And 5, 4, 3, 2, and 1. We're going to go ahead and get started. So topic 3.4, looking at buffers and titrations, and then jumping into our second final chapter, chapter 4. That is our plan for today. Last class, we introduced the topic of titrations, an experimental procedure to figure out the concentration or the amount of something in our Erlenmeyer flask. And in this flask, we have, for this experiment, an acid or a base, and then we add drop by drop from our burette an acid or a base. And we set up the experiment so that we choose an appropriate indicator, something that will change color when we've added just the right number of moles to just the right number of moles of acid. A titration with an acid base is when we have a strong acid and a strong base, such that it produces spectator ions, and the pH at the equivalence point would be 7. But then we went to more interesting examples of a weak species with a strong species. And we're on our final example now of a weak base being titrated with a strong acid. We're starting this experiment with our titration curve here. We're adding some strong acid from our burette to the weak base that is in our Erlenmeyer flask. We have a pH meter inside the Erlenmeyer flask to tell us what the pH is at every point along this titration experiment. Then we've also added an appropriate indicator that will change color. In last class, we talked about how the indicator is actually a weak acid itself. And whether or not it has its proton in its protonated form or has lost its proton in its non-protonated form, that causes it to change color. And we want to choose an indicator that changes color around the pH point where we're expecting our titration to have that pH at the equivalence point. We can plot out our experiment starting with 0 amount of our strong acid and add drop by drop to the weak base in our Erlenmeyer flask. So we start out with quite a basic pH because we only have the weak base in our Erlenmeyer flask. And we add drop by drop by drop by drop, and I'm going to go right about to this point here. At this point, I'm halfway to the equivalence point. The equivalence point, as we know from last class, is when we've added just the right number of moles to equal just the right number of moles of acid. So the acid and base number of moles are equivalent. When we're halfway there, that means we've added half the amount of strong acid to get us to the end of our experiment. So let's say that we started with n moles of our weak base in our Erlenmeyer flask. And I'm going to add half the number of moles to get me to that end point. Well, an acid and a base react completely. So if I react all of this strong acid, I'm going to have none left. If I react exactly half of my weak base, I have half of my weak base left. This reaction produces half the amount of the conjugate acid salt. At this point, I can analyze what I have floating around inside my Erlenmeyer flask in my solution. I have some weak base, and I have some conjugate acid. By definition, this is a buffer solution. This region right in here is defined as the buffering region on our titration curve. It has a slow change in pH. It's very gradual, even though we're adding strong acid. It's a gradual change because it has the weak base and the conjugate acid. It has a buffering effect on the change in pH. When we looked at the strong acid, strong base titration, it was basically flat, sharp, and flat, or it started. We can recognize this weak, strong titration because it has this gradual buffering region. Now, when we get to our equivalence point, so let's go from here. So we started with 0 amount of our strong acid. We added drop, 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 and we got to the midpoint. The midpoint is when we're halfway to the equivalence point. We've added half the amount of strong acid that we want. Now we're going to go drop, 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 and then we're going to stop when there's a color change. And we've selected our indicator to change color at just the right point. So that means if I started with n amount of moles of my weak base, that means I've added exactly n amount of moles of my strong acid. An acid and a base react to completion so that I have no more weak base, no more strong acid, but I have produced some conjugate acid. The pH at the equivalence point for this particular titration is acidic, not because of the strong acid present, but because we have reacted this strong acid with the weak base to produce this conjugate acid salt. If we continued with our experiment, so now we're at the equivalence point. The equivalence point is the steepest part on this titration curve. The middle of that steepest part tells us where that equivalence point is. And we can predict that equivalence point based on the salt that is produced. Ideally, this is when the color change happens. But then we could keep adding drop by drop by drop more and more and more strong acid. And then you can see the pH drops predictably to a strong acid pH. And then it's fairly flat because we have excess strong acid in our solution. So a thumbs up question, not quite an eye clicker question yet. We have those coming up. Which indicator would be a suitable choice for this weak base strong acid titration? I'll give you 20 seconds to chat with the person beside you, and then we're going to vote. Okay, and we are going to go ahead and vote. Who votes for A, the bromophenol blue? Who votes for B, methyl red? C, phenolphthalein? D, any of the three? And E, none. Okay, well done. Methyl red is the correct answer. The idea is to choose an indicator that will change color right at that equivalence point, within plus or minus 1 of that equivalence point. The pKa can help us decide that. So we want a plus or minus 1 of the pKa of the indicator to match that equivalence point. So well done. Okay, so we're going to analyze quantitatively now this experiment that we've just discussed. So we have our weak base in the Erlenmeyer flask, and we're adding drop by drop this strong acid. In order for us to have the measurements of this experiment, there's also a pH meter that's measuring the pH, but more than likely, we're going to add a drop or two of our appropriate indicator, the methyl red. Part 1A. We're just going to do part 1 of this question. A, B, and C are like 8 slides long already, so that's what we're going to do today. We want to figure out the pH after we've added 20 milliliters of hydrochloric acid. So we need to pay attention to what we're starting with. We have 25 milliliters of a specific concentration of our weak base in our Erlenmeyer flask. Adding drop by drop by drop until we stop at 25 milliliters, or at 20 milliliters of the strong acid. So that's somewhere around here. We've only added 20 milliliters. I can tell you from calculating this before, we haven't quite reached the equivalence point. But we want to analyze the pH at different points along this experiment. So my question for you, our first clicker question today, which reaction must be analyzed first to solve this problem? Chat with the person beside you for 20 seconds. Okay, and 10 more seconds to get your answer in. And 3, 2, and 1. We'll give it a second. Okay, so we have a distribution here. Most votes for B, and B is the correct answer. Well done. Okay, so this is correct. When we're analyzing systems that will set up an equilibrium, the first step is to do the direct reaction. The direct reaction to make the buffer, the direct reaction to dilute something, direct reaction for anything, and then step 2 is to set up that equilibrium. If you try to set up the equilibrium first, it's not going to work. So step 1 is always that direct reaction. If we have an acid and a base that can react together, they must react to completion. Now, it would have been equally correct to react NH3 plus H plus. If we had written it out that way, that would have been fine. If we had written it out as H3O plus, that also would have been just as correct, as long as it was balanced. D is incorrect because it's not balanced. Here we can see we have a total of 6 hydrogens on the left and only 5 hydrogens on the right. So NH3 reacting with H3O plus will make NH4 plus and H2O. That would be a legitimate option as well. HCl is a strong acid, so it will completely ionize to produce H plus and chloride. We can write just that H plus, that's fine, But we also know that H plus will tag along with a water molecule. And H plus H2O makes H3O plus hydronium. So we need to be able to recognize that these three different ways of talking about an acid are all legit ways. We just need to make sure that our reaction is balanced. So step one is that direct reaction. The NH3 reacting with the strong acid, HCl, H plus, H3O plus, to produce our conjugate acid. Well, we want to figure out the pH. So we need to know how much of the weak base is left over once it reacts with this acid. We start with 0 amount of our conjugate acid, but I'm going to need to calculate the number of moles of NH3, the weak base that I started with, and the number of moles of HCl that I started with in order to figure out the limiting reagent and what's left over. So for the weak base, I have the volume. We started with 25 milliliters and the concentration. If I multiply those values together, that will give me the number of moles. I'm going to put 25 milliliters into liter units so that it factors out with my molarity. Molarity is moles per liter. The number of moles of acid at this point, we've added 20 milliliters of 0.2 moles per liter. So I have 0.01 moles and 0.004 moles as my starting values for each of these components. It's a 1-to-1 ratio in my stoichiometry of this balanced equation. So I can see that the hydrochloric acid, or H+, is my limiting reagent. So it will completely react until I have none left. I'll lose that same amount of my weak base because it's a 1-to-1 molar ratio. And it's a 1-to-1 molar ratio to produce the NH4+, so I will produce that same number of moles of my conjugate acid. I can then analyze what I have left. I have some weak base. I have some conjugate acid. This tells me that I have a buffer solution. I'm in my buffering region at this point. I have not yet reached the equivalence point. I haven't added enough acid to match the amount of weak base in the solution. But my job right now is just part A to figure out the pH at this point in the experiment. So I now have the number of moles of weak base and the number of moles of conjugate acid hanging out in solution. So what is the next reaction that I need to analyze to solve this problem? This is going to be a hand-waving example. So chat with the person beside you for 20 seconds. Okay, we're going to go ahead and vote. Who says it's A? Put up your hand. Who says it's B, C, D, and E, and A? Well done. So A is the correct answer. I did have some votes for C, but you know what? We don't have any H3O plus or HCl to react with right now. We used up all the hydrochloric acid. So any meaningful concentration of it, we don't have at this point. So we simply want to set up the equilibrium of the weak base with its conjugate acid. And as I've mentioned before, it's always easiest to put the parent species on the left-hand side. The parent species is the one that's not the conjugate acid or base. So we have a weak base solution with a conjugate acid, or a common ion of this conjugate acid. We've already determined the number of moles that we have of each piece. It's a buffer solution. For a buffer solution, I have the option of comparing concentration units or moles. I already have moles. For simplicity, I'm just going to compare the number of moles, because both of these mole values are divided by the same total volume. So for simplicity, I'm going to move forward with the number of moles. I'm going to rewrite the number of moles of my weak base and the number of moles of my conjugate acid. And I'm starting with 0 amount of my hydroxide. I'm going to lose a little bit of X, gain a little bit of X, and gain a little bit of X. The shift in X is going to be small for my weak base and my conjugate acid because it's a common ion problem, or a buffer problem. So I can now analyze my Kb expression and solve for the concentration of hydroxide. And we remember that's products over reactants to the power of their coefficients. Water is a liquid, so it doesn't show up. We can get away with using moles instead of concentration units because it's a buffer. The Kb we pull from another question. This is something that we could look up in our data table, the Kb of NH3. Therefore, the concentration of hydroxide at equilibrium, that X value, is 2.7 times 10 to the negative 5. I can take the negative log of that value to calculate the pOH. That's the pOH, but on this graph I have pH, which is 14 minus the pOH value. So therefore, when I've added 20 milliliters of my strong acid, I've formed a buffer. I have not yet reached the equivalence point. We still have a basic pH, and we can plot it accordingly here. So this is part A of our problem. After we've added 20 milliliters, we're just starting our experiment, we can still see a basic pH value. So now we're ready to move along to part B. Part B, what is the pH at the equivalence point? Well, we can see on our graph, we can predict that it's going to be pretty close to a pH of 5. But we need to actually be able to calculate that exactly. When we're doing a problem with the equivalence point, we have to know how to interpret what that value means. If we're at the equivalence point, that means we've added just the right number of moles of acid to equal the number of moles of base that we started with in our Erlenmeyer flask. On the previous slide, we calculated the number of moles of base using the starting volume and the starting concentration, and it gave us 0.01 moles of our base. At the equivalence point, based on the balanced stoichiometry, we know that this same number must be the number of moles of HCl that we've added, which of course is the number of moles of H+ ions that we've added. So we can go ahead and write out this direct equation again, just like we did in the first step, but now the amount of H plus or HCl is different. We've added more, and we're going to analyze from the start to the equivalence point. So therefore, we have conjugate acid. We have no weak base. We don't have a buffer solution anymore. We're going to need to set up an equilibrium expression based on this conjugate acid salt. I know the number of moles, but in order to analyze the equilibrium that is set up with this conjugate acid, I also need to know its concentration. I've done the direct reaction to produce this conjugate salt, but I need to know its concentration for its equilibrium analysis. Concentration is number of moles over total volume. I know the number of moles that I've produced because we just calculated that based on the stoichiometry. The total volume includes the volume of the weak base that we started with, but it also includes the volume that we needed to add of the hydrochloric acid. What is the volume of that hydrochloric acid? We know we added 0.01 moles worth. We know that the acid was added in a 0.2 mole per liter concentration. I know the number of moles and I know the concentration. Therefore, I can solve for the volume of HCl that I added. We can calculate this using unit analysis, or we can remember that concentration is moles per unit volume, which means volume is moles divided by concentration. I need 0.01 moles of my strong acid. It comes from a concentration of 0.2 moles per liter. Therefore, I must have added 0.050 liters, or 50 milliliters, of my hydrochloric acid. These two values together, the starting 25 milliliters and the 50 milliliters of strong acid that I added, combine to make the total volume of the solution now in my Erlenmeyer flask. I can take the sum of those two volumes and then take 0.01 moles and divide it by that total volume. Therefore, I'm starting now with a concentration of 0.133 moles per liter of my conjugate acid. And this is now a conjugate acid-salt problem. It's not a buffer. I don't have weak base. I don't want to start with the parent weak base on the left because I don't have any of it. So I need to set up an equilibrium with my conjugate acid on the left. My conjugate acid, it's an acid. Acids donate a proton. It's going to react with water to produce, not H2O plus, H3O plus. There we go. NH4 plus reacts with water, donates a proton to produce H3O plus. The starting concentration here is 0.133 moles per liter. I'm starting with 0 amounts of my products. I'm going to lose a little bit of X, gain a little bit of X, and gain a little bit of X. This is now a weak acid problem. We used the Kb when we were analyzing the weak base equation. We now need to use the Ka to analyze this weak acid problem. We've calculated the Ka for this conjugate acid previously by using Ka times Kb equals Kw. So we're going to pull that value from a previous problem. And it's products over reactants to the power of their coefficients. X is therefore 8.6 times 10 to the negative 6, which is the concentration of H3O plus at equilibrium. We know that pH is the negative log of that H plus or H3O plus concentration. Therefore, the pH is 5.066, which is certainly very close exactly to this pH 5 that we predicted. Okay, so we have solved the pH just before we reach the midpoint. We have solved the pH at the equivalence point. Our final step for this problem is what happens when we add 65 milliliters of HCl. What happens when we overshoot this endpoint? We had a color change, and then we just kept adding more and more. So step one, again, is to react the acid with that base. This is the final slide of this problem, I promise. What if we added 65 milliliters of HCl? Let's go ahead and calculate the number of moles. We already calculated the starting number of moles of NH3. We're solving this problem as if we're starting from the beginning again. So we're starting with that 0.01 moles of NH3, reacting with excess H+. Now we have more H+ than what we needed for this experiment. That means the NH3 is now our limiting reagent. It will completely react until we have none left. It's a 1-to-1 ratio. So we will have 0.030 moles of our strong acid left. We now have a conjugate acid, just a little bit, and we have a strong acid coexisting in this solution. Well, we've analyzed a problem like this before, at least qualitatively. If we have a strong acid and a weak acid present, the strong acid is going to determine the pH of the solution because it will completely ionize. This 0.003 moles is the number of moles of H+ that exists. Did I miss a zero somewhere? NH4 plus concentration. Thank you. Yes, you're right. 0.01. There we go. That's right. Thank you for watching that stoichiometry. So we reacted 0.01 moles, so we produce 0.01 moles. You are correct. Thanks for catching that. But it's still true that we have some strong acid left. Even though it's only a little bit, the pH is going to be determined by the concentration of this strong acid. The concentration of this strong acid is the number of moles of the strong acid divided by the total volume. I've calculated that I have 0.003 moles of my H+ in solution. I started with 25 milliliters, and I've added 65 milliliters, 0.065 liters, which gives me a concentration of H+ as 0.0333 moles per liter. The pH is the negative log of the concentration of H+, which gives me a pH of 1.48, which is quite acidic, just based on the excess H+ that we had left over. Now, you might be interested, what if we did analyze the equilibrium from this weak acid? I would sometimes do this. You can do this on your own. When you do this on your own and set up the equilibrium of NH4+ reacting with water with H+ as the common ion, you're going to come up with exactly the same pH value. Okay, so we're going to save ourselves some time, save ourselves a few finger cramps, and just stop here. Okay, so the pH is determined by the excess strong acid, and you're more than welcome to go and double check that answer. So well done. We're going to wrap it up with part 1 here rather than going to part 2, because I want to jump onto chapter 4 today. So my question for you, now that we have analyzed weak acids and weak bases and buffers and titrations and set up all these equilibrium problems, we're now shifting to a new unit to analyze electrochemistry, redox reactions, and batteries. If you were designing a battery, what factors would you consider? Type in 1. It looks like we've definitely had some technical issues, but this is a word cloud from a previous class. I know, this is just not cooperating for me here, but we'll see if we can recover this one. So when we're trying to figure out what we would care about for a battery, we would want to consider things like efficiency. How fast does it take to charge? How long does that charge last? What voltage is required to drive the electrons to actually run our cell phone? What type of reaction needs to happen? What type of materials need to be in this battery? How toxic are those materials? What do we need to do to dispose of those materials? What's the safety of this battery? How much energy does it have? These are all the questions that we want to explore when we talk about redox reactions. In chapter 4, we're looking at reactions that involve a reduction and an oxidation. A redox reaction requires that something is reduced and something is oxidized. In order for us to analyze a battery, or for you to develop a more efficient battery, we need to understand the redox reactions that are occurring inside of a battery. We need to understand what's happening so that we can make it better. We have big lead acid batteries in our car, and they're about this big by this big, and they have sulfuric acid sloshing around in them. For a robust car, well, it is a robust battery. We need a robust battery for a car that can bounce along a road, and a car is big and heavy, so it's okay that this battery is big and bulky. But it's reliable. It works in Canadian winters and Canadian summers. But in my cell phone, I certainly don't want to have a lead acid battery with sulfuric acid sloshing around in it. I don't want to have to stick that in my back pocket. I want something small, something efficient, something that can last all day. Redox reactions, reactions where something is reduced and something is oxidized, are what are responsible for making batteries work. In this unit, we want to assign oxidation states so we can figure out what's being oxidized and what's being reduced. We want to be able to figure out how to calculate the potential of a cell. What's the difference between the reduction and the oxidation half reactions? How big is that potential difference that will cause the electrons to flow and produce electricity? Or if it's a redox reaction that we really want to make happen, we can apply voltage and cause a redox reaction to occur, even if it wouldn't have happened spontaneously on its own. In this unit, we want to be able to calculate that cell potential, and we want to predict what that means, understand what that means. Is that reaction spontaneous? A battery reaction has to be spontaneous, or else it wouldn't be worth anything. It needs to spontaneously happen. So we need to be able to predict mathematically and with chemistry what makes that spontaneous reaction. What happens if the conditions are not standard conditions, like Canadian winters with different temperatures? All of this starts with an understanding of oxidation states and oxidation numbers. And once we know those oxidation numbers, to balance redox equations. So this is what we're looking at topic 4.1. For a redox reaction, something is producing electrons and something is gaining electrons. We could assign oxidation states, like to iron, and see that iron is going from an oxidation state of 0 to +2 and losing 2 electrons. These 2 electrons then pass over to H+ and produce hydrogen gas. So when we come back on Wednesday, we're going to figure out how we assign these oxidation states and balance some equations. Thanks for your cooperation. Have a great day.